Today in the workshop, we're checking out the TF-Luna LiDAR sensor. We'll see how the TF-Luna works and how to use it with an ESP32 and Raspberry Pi Pico. We'll also use a Windows utility to change the sensor's parameters. We're going the distance today, so welcome to the workshop. Well, hello and welcome to the workshop, and today we're going to be working with a real cool little time-of-flight LiDAR sensor called the TF-Luna. Now the TF-Luna is actually a cousin of a LiDAR sensor we worked with several years ago, the TF-Mini, but it's a much more advanced device. It's capable of sensing things to a distance of up to 8 meters, and it can resolve things down to about 1 centimeter. You can use it with either serial or with I2C, and today we're going to use it on 3 different platforms. We're going to check it out with an ESP32 running C++. We'll use a Raspberry Pi Pico under MicroPython, and amazingly enough, we're going to begin using Microsoft Windows because Bebewake, the manufacturer of this device, has created a utility that runs under Windows that not only displays the data from the Luna, but allows you to reset its parameters. So let's learn everything we can first about the TF-Luna LiDAR sensor. The TF-Luna is a single-point time-of-flight ranging LiDAR unit. It has a range of 20 centimeters up to 8 meters. Within that range, it can resolve a distance down to an accuracy of 1 centimeter. The TF-Luna has an adjustable frame rate from 1 to 250 Hz and can resist ambient light up to 70 lux. The power supply voltage for the LiDAR sensor is 3.3 to 5 volts. However, this is a 3.3 volt logic level device, so don't apply 5 volt logic to it. It has an average current draw of less than 70 milliamperes, and it can also be run in an ultra low current mode. The peak current draw is 150 milliamps. The TF-Luna can communicate using I2C or serial UART communications. The TF-Luna is what's known as a time-of-flight or TOF sensor. With a TOF sensor, a light beam is sent from the device. It reflects off of the target and is reflected back to the sensor. The beam travel time determines the distance. As light travels very quickly, the TF-Luna measures the phase shift between the two beams. All of the distance calculations are performed on board the TF-Luna. Therefore, it can provide a completely calculated distance to your microcontroller or microcomputer. The TF-Luna has a 6-pin connector on one side, and the pinout is as follows. The first pin is the power pin, and this can be anywhere from 3.3 to 5 volts DC. The second pin has multiple functions depending upon whether the TF-Luna is operating in I2C or UART mode. In UART mode, this is the receive line, and in I2C, this is the serial data or SDA line. In a similar fashion, pin 3 is also used for different functions. In the UART mode, this is the transmit line, whereas in I2C, this is the clock or SCL line. Pin 4 is the TF-Luna ground. Pin 5 is the mode selection pin that determines whether the device will operate in I2C or UART mode. If the pin is left alone or pulled high, the device will be in serial UART mode. This is the default. If it is pulled down to ground, it'll be in I2C mode. The 6th pin is the multiplex pin, and it has dual functions as well. In serial UART mode, it's a simple on-off signal that can be triggered at a preset distance. In I2C mode, this is a ready line that goes high whenever there is data available on the TF-Luna. The TF-Luna can be operated in both the UART and I2C mode. In UART mode, the mode pin is not connected or held high. The default speed is 115/200 bits per second, with 8 data bits, 1 stop bit, and no parity, and you can adjust these parameters within the TF-Luna. In I2C mode, the mode pin is grounded. It has a maximum data transmission speed of 400 kilobits per second. The default I2C address is hexadecimal 10. However, it has an address range of hexadecimal 08 to 77, and again you can program it for a different I2C address. In both modes, the TF-Luna will deliver 3 different pieces of data: the distance in centimeters, the the strength of the signal, and the temperature of the internal chip. You can change the parameters in the TF-Luna by writing to its internal registers. You can do this through your own code, or you can use an updater utility for Microsoft Windows that's available for the TF-Luna. The TF-Luna LiDAR unit is one of a series of LiDAR units with various specifications. Some of these units can actually work to a distance of 1.2 kilometers. One advantage of choosing the TF-Luna as your LiDAR sensor is that Bebewake provides extensive documentation on their website for the unit, as well as test software. So now let's go examine the TF-Luna LiDAR unit. And here we have the TF-Luna along with a couple of connecting cables that are provided with the device. And as you can see, it's a pretty tiny little device. You've got the two windows here for the send and receive IR. And on the bottom over here, we can see the connector that we connect to, the 6-pin one. The back of it is just a circuit board, and there's nothing really to do with it over here. And as you can see, there are two little mounting flanges on it so that you can mount this thing really easily. It comes with a number of connecting cables, including ones with male and female ends. This is a female end one over here. And this is also a cable you can use to connect it to a Pixhawk or another controller like that, because it can be used with those as well. So all in all, a very simple little device. And as we're going to see, it's also a pretty simple device to use. Okay, at the beginning of the video, I told you that we would be testing this out with a utility that Bebewake provides for use with Microsoft Windows, and we're going to start off by doing that. Now, you can get this utility from their website. The link is in the article that accompanies this video, and at the same time, you can also download some documentation for the TF-Luna as well. They've got some excellent documentation for it. Of course, you're going to need to connect this to your computer, and you'll notice that the TF-Luna doesn't have a USB port or anything on it, so you're going to need another piece of hardware. What you need is a TTL to USB converter, also known as an FTDI adapter. Now, you may already have one of these around. If you've used an ESP32 cam or something, you required an FTDI adapter to program it, and that will be absolutely fine. So let's see how we hook up the FTDI adapter, and then we'll hook this up to Microsoft Windows and see what we can do with it. To connect our TF-Luna to our computer, we will of course need the TF-Luna unit, as well as an FTDI or USB to TTL converter. Now, these are available with different voltage ranges, and what you need is a 3.3 volt one. Some of them can be selected between 3.3 and 5 volts. Make certain that yours uses 3.3 volt logic, because the TF-Luna does not support 5 volt logic. We'll begin by connecting the power on the TF-Luna to the VCC pin on the FTDI adapter. The receive pin on pin 2 is connected to the transmit pin of the FTDI. The transmit pin on the TF-Luna is connected to the receive pin on the FTDI. And the ground from the TF-Luna is connected to the FTDI ground. We leave the mode pin disconnected because we want to run the TF-Luna in serial mode, and we have no reason to connect the multiplex pin. We'll connect the USB connector to our computer, and our wiring is finished. We'll be using a GUI utility from Bebewake in order to test our TF-Luna LiDAR. Let's see how we do that. And so I have my TF-Luna connected to the FTDI adapter and a cable which is running off to my computer, so it's a pretty simple setup over here. And if we look at the Bebewake LiDAR GUI viewer that we've downloaded, we can see that it's got a lot of interesting looking controls. Now, the first thing you need to do is select which unit you're going to use. And I've got a TF-Luna because this is compatible with all of their LiDAR units. And the COM port, and in this case it's COM8, but it might be different on yours, of course. The baud rate is correct at 115/200, so I'll hit connect. And you see we get a graph here, and if I move my TF-Luna around, the graph shows me the distances, and so the TF-Luna is working. And this, of course, is one thing you can do with this utility, but there are a number of other things you can do as well. You can set the parameters in the TF-Luna. You can hit the frame rate. You can change that if you wish. You could change the baud rate if you like, set it into command trigger mode. You can save the setting when you're there. You can read out the firmware version of the TF-Luna. And down over here, there's a few things too. First of all, in the very bottom bar, you can see that is always measuring the distance and the signal strength. But over here, the function is very neat. It's a command, custom command, and there's a number of different things that you can do. You can change the I2C address, for example, if you wanted to, and you would select that, and then you would add the parameters, and you'll have to take a look at the documentation for each of these to see what parameters there are. Not all have 3 parameters. It shows the command string that you're going to send over here to the unit, and then you can just send that. So if you want to modify the configuration of the TF-Luna, you can do it through this utility. So it's a great utility not only to test out the TF-Luna, but to also see and change different settings in it. So now that we've seen that, let's move on to use the TF-Luna with a couple of microcontrollers. Okay, now that we've checked our TF-Luna out under Windows, let's move on to the ESP32. Now I'm going to be using an ESP32 S3 dev kit, which is a really big ESP32 module that also has 2 USB ports on it, but you could use any ESP32 for this experiment. In this experiment, we're going to run the TF-Luna in I2C mode, so we'll be grounding its mode pin. So let's go and take a look at the code and the hookup for the ESP32 and the TF-Luna. Now for this experiment, we'll need the TF-Luna, and we will need an ESP32. Now I'm using an ESP32 S3 dev kit, but pretty well any ESP32 microcontroller will work. If your ESP32 does not have the same GPIO pins that I'm using, you can use alternate pins and just change the code. At any rate, we'll start off by wiring the power on pin 1 of the TF-Luna to the 3.3 volt output of the ESP32. Now you could also use the 5 volt output, as both will power the TF-Luna. Pin 2, which is SDA in the I2C mode, is connected to GPIO pin 17. Pin 3, which is SCL, is connected to GPIO pin 16. The ground on the TF-Luna is connected to one of the grounds on the ESP32. And the mode line from the TF-Luna needs to be grounded as well. This will put the device into I2C mode. The multiplex pin on the TF-Luna is not used in this application. And that completes the wiring. Now let's go take a look at some code we can use with the TF-Luna and the ESP32 in I2C mode. Now here's a sketch that we're going to be using with our TF-Luna device. Now one thing we normally do with our sketches is grab a library that will handle our device, but there aren't really very many libraries made for the TF-Luna. There is one that's in alpha and it doesn't include any example code, so I've decided just to use the wire library and do this manually, which is a common way of talking to the TF-Luna. So we'll include the wire library for the I2C operations, and we'll define our I2C connections over here. Now if you've used a different ESP32 and needed to use different GPIO pins, you can change this to match whatever you've wired it up to. Then we have a couple of communication parameters that we've defined over here, and a buffer which we've already preloaded with some values, and these are values you send off to the TF-Luna to essentially wake it up. So this is also something that we saw when we looked at the Windows application. You might have noticed this was down in the boxes below. At any rate, in the setup, we'll initialize the I2C and the serial port, and then we'll go into the loop. Now in the loop, we'll begin transmission to the I2C address, which is the default 10, unless you change your TF-Luna. And we'll send the instructions from the buffer, and this is what we do. We write that. 5 is just the length of the data that we're sending, and then we'll end the transmission. And so now we've woken up the TF-Luna, so to speak. We can start requesting data from it. So we'll do a request from the address at the data length, which we've defined as 9, and we'll create an array to hold all that data. We'll define a few variables in order to represent distance, signal strength, and the temperature of the chip, and also a couple for checksum and index. Then we will read our data into the array that we've created, and if the data is complete, in other words, if the index is equal to the data length and none of it is dropped off, then we'll extract the values for distance, strength, and temperature. And finally, we just print those values to our serial monitor, insert a short delay, and do the whole thing over and over again. So it's a relatively simple sketch when you break it down. Let's load it up to our TF-Luna and watch it work. Okay, so here's my TF-Luna hooked up to a ESP32 dev module, And I'm just bouncing it off of things in the workshop, and so I can move it around to bounce it off different things. Now, if we look at our serial monitor, you can see that we're measuring a distance of about 73 centimeters to whatever it's bouncing off of. The signal strength and the chip temperature, let me just move this around a bit, and you can see the readings instantly change. One thing that's impressive about this when you compare it to things like, let's say, ultrasonic sensors is how fast you can get a reading out of this thing. It's really very, very quick. So if you need instantaneous responses, this is probably a very good choice. But as you can see, this seems to work pretty well with our ESP32. So now that we've seen the ESP32 work with the TF-Luna, it's time to bring in a Raspberry Pi Pico, and we're going to change a couple of things around for this experiment. First, we're going to use the Pico in MicroPython instead of C++, and we will use the TF-Luna in UART serial mode instead of I2C. So let's go and see how we hook this up, and then we'll look at some MicroPython code to work with the TF-Luna LiDAR sensor. For this experiment, we'll of course need the TF-Luna LiDAR unit, and we'll need a Raspberry Pi Pico. Now I'm using the original Raspberry Pi Pico, but you could use a Pico W, a Pico 2, or a Pico 2W. Just remember we're using MicroPython, so you'll have to get the correct image for your particular Raspberry Pi Pico from the MicroPython website. We'll begin by connecting the power, which is pin 1 on the TF-Luna, to the 3.3 volt output on the Raspberry Pi Pico, and that's on pin 36. Pin 2 on the Luna is the receive pin because we're using it in UART mode, and we're going to connect it to the UART1 transmit pin, which is pin 11 on the Raspberry Pi Pico. Note that despite the fact that this is physical pin 11, it's actually GPIO pin number 8, and you'll need to know that for our code. In a similar fashion, the transmit line on pin 3 of the TF-Luna is connected to the UART1 receive line on pin 12, which is really GPIO pin 9. And the ground on the TF-Luna will be connected to one of the grounds on the Raspberry Pi Pico. These are the pins that have the square shape instead of the rounded one. The mode pin is not connected as we're running in serial mode, and we have no need for the multiplex pin. And this completes the wiring. Now let's install MicroPython onto our Raspberry Pi Pico and write some code to use it with the TF-Luna. And here's the MicroPython code that we're going to be using with the Raspberry Pi Pico and the TF-Luna LiDAR sensor. Now this may seem long, but that's because there's a lot of comments in the code so that you can understand it. Now we're going to start off by importing some important libraries, and then we define two different UARTs, and that may seem a little bit odd because of course we have one internal UART, UART1, which is connected to the TF-Luna, but what's the other UART? Well, as it turns out, the other UART is the USB port, and so UART1 is the one that we connected to the TF-Luna. Note that it's GPIO pins 8 and 9. Remember, those aren't the same as the physical pins, and if you decide to use different pins, you can just modify this. UART0 is, as I said, the internal UART that talks to the USB port, and that's over here. Then we write a function called getLiDARData, which starts off by initializing an empty byte array for the incoming data, and we check to see if we have any incoming data on UART1, which is connected to our LiDAR sensor. If we do have data, we have to read 9 bytes because that's the TF-Luna data packet. And so basically we're going to read 9 bytes, and we're going to check the first byte to see if it's hexadecimal 59 because that's the packet start identifier, and it makes certain that we have a legitimate packet. Assuming we do, we can calculate the distance, the signal strength, and the chip temperature, and you'll note that this is done identically to the way that we did it with the C++ and ESP32. And so we basically get those 3 values, we write out those 3 values to UART0, and then display them on the console over here, all nicely formatted, so we see the distance, the signal strength, and the chip temperature. We allow a brief period to sleep, and then we start all over again. And so basically we run the program down here while everything is true. We call getLiDARData, and then we put a little delay between the readings, and this is set for a 100 Hertz update rate. So if you change the update rate on the TF-Luna, you'll probably want to change that. But otherwise, it's a relatively simple program. Let's put it onto our Raspberry Pi Pico and watch it work. And so here's our TF-Luna connected to the Raspberry Pi Pico. And once again, we'll just do a demonstration by moving everything around. One thing I had noticed, let me see if you can see that. Yeah, do you see inside there? You can actually see the transmitting LED or laser when you aim it at the camera over there. So you can actually see if your TF-Luna is working sometimes just by looking at it. But if we look at the screen as I move it around, once again, I'm getting different distance readings, signal strengths, and the temperature of the chip. So basically the same readings we were getting with the ESP32. So as you can see, you can easily use the TF-Luna with MicroPython with a Raspberry Pi Pico or pretty well anything else that runs MicroPython. Okay, that wraps up our look at the TF-Luna LiDAR sensor. I hope that you enjoyed it, and I really hope that it's inspired you to think of a few projects in which you can use this really incredible little device. Now, if you want some more information about the TF-Luna, if you want the links to download the software that I used earlier under Windows, you'll find all of that on the article that accompanies this video on the dronebotworkshop.com website, and there is, of course, a link to that article under the video. While you're on the website, if you haven't yet, please consider signing up for my newsletter. It's not a sales letter. It's something I just send out every now and then to let you know what's going on here in the workshop. And of course, it's free to sign up. I just need your email address. I don't even need your name. But if you are willing to give me your name and email address, then you should sign up for the DroneBot Workshop forums. If you want to learn more about the TF-Luna or any other electronic component or just talk shop with a number of like-minded individuals, the forum is a great place to go. I just need your email address and your name and a really cool username, and you're on the forum. And of course, if you haven't yet, please subscribe to the YouTube channel. I love getting new subscribers and would love to make you the next one. Subscribing is a very easy thing to do. All you need to do is click on that red subscribe button. And if you also click on the bell notification, you'll get notified every time that I make a new video, which hasn't been a lot lately, but I'm sure the frequency is going to get a lot quicker after this. And so until the next time that we meet, please take care of yourself, stay safe out there, and I will see you soon here in the DroneBot Workshop. Goodbye for now.